So what I would like you guys to do, and you guys as well, go to that equipment folder and try to locate this thing that's called equipment 3, okay? And double click on it so equipment will start working. Yeah, so you should be also seeing something like this. All right. Okay, now we will go to the left corner and say start. Okay, so that's the thing that we're going to hit. And it should make this portion white out. This couple of things to remind you. Now, this side here is the pressure history. As the name says, this is just a gauge and showing you the pressure as time is going on, okay? So I'm now seeing 760 from each one of these gauges. I have several gauges here. Look at the gauges. These are pressure gauges. You hopefully can see my mouse cursor nicely. And this is going to be our reaction chamber. That's going to be a chemical vapor deposition reaction chamber, this one here. And I have some valves and some pumps to work with, all right? All right, now, we will start with the most fundamental thing. We'll just open the mechanical pump like you guys must have done in the lab by clicking on this little button here that I'm emphasizing. So turn it on, and then once after that, you will see the pressure change here on the pressure histogram, and also see the change on this gauge here as well, okay? So we are turning on the mechanical pump. As we're doing that, the pressure is dropping down and got stabilized. Hopefully you guys can see it too. Did you see that on your screen? Everything worked out? Okay, good. So this is what we call the base pressure, and that's where we reached. You guys worked it out too? So we have now pumped down this bypass line, this little line. They have, just like electricity, they have their own conductance. So if the lines are small, their conductance is low. If the lines are large, their conductance is large, okay? That will determine the time to take this all pump down to the base pressure. What do I see here? Does it go below 2.3? No, that's millitorrs, right? 2.3 millitorrs. Why? I'm not surprised, because mechanical pumps can only take you down to 2. Like these kind of 10 to the -3 range. Do you guys remember from the first week? That's the level where the mechanical pumps can take you. That's why they're called the roughing pumps, because that's their main idea. It's just an intermediate level pump. Okay. Now we're going to try to pump down the reaction chamber over the mechanical pump. Which valve should I open? I should open this VV valve, right? I'm going to open this bypass cut valve, and then I have another gauge here from the reaction chamber, this one here. I'm going to see the pressure change on this gauge. Now, let's do it together, and let's observe how long it will take. As soon as I open it, of course, this was vented, so it jumped up to somewhere intermediate. It didn't go up to all the vent. Did you guys see that? So because this was vented, the large chamber was vented. Now it's taking much longer. You guys observe? Why is it taking much longer? Because now the volume has changed drastically, right? This reaction chamber is much bigger. So it's taking me a lot longer than it took before just to pump down this little bypass line. So in a regular process, this is what you would do. You would start to pump down the chamber after loading your samples, of course. This is after loading your samples. Okay, now we're at the 0.1 torr range and going down. The next thing we're going to do, we're going to close the bypass valve pretty soon. So once this reaches down to the and stabilizes at the base pressure, I know that 2.6, right? 2.6 millitorrs. I will close this valve here. I'm very close. Yeah, let's close this valve right now. So since there is no leaks in this ideal world, what happens? It stays at 2.4 millitorr. Do you guys observe that? It doesn't change. Norfolk guys, can you follow me what I'm doing here? So I just close this valve here, and this reaction chamber, I can see them on my monitor. You guys, I just closed the yeah. So that's the copy place I was talking about on the bridge. Right now, I mean, Marvin would say, oh, this is too ideal. You never have this kind of stabilized pressure. There's always a small leak somewhere, right? So this is the ideal world. We have no leaks, nothing, so good. Everything is perfectly working. Now, I'm going to prepare my turbo. Do you guys remember that? The mechanical pump is just an intermediate, like a first level pump. So I need to introduce my main pump, the turbo pump. So I will open this V1 valve, and I will open the connection between the two. All right. What did I do? I opened this valve, and now both the turbo and the chamber, both the turbo and the chamber, they're both below the crossover pressure. Crossover pressure was what? The switch between mechanical to turbo pump range. Turbo pump will not work because there would be too much of a load on the turbo pump blades. I would just kill the blades of the turbo pump, remember? So now I can safely open up the turbo pump as well. Once I do that, look at the pressure change. The pressure go down to 4.410 to the -9. That's like another ridiculous number. In this ideal world, everything can happen nicely. Yeah. Now, this line here is still millitorr, but this turbo pump started working, and it took it down to 4.4. Okay. Now I am ready to open up this intermediate valve. This is what's called that. What was it called? Can anyone remember? This one connecting the turbo to the main chamber. You guys probably haven't seen it yet, but Norfolk people must have seen it. This is the valve that's connecting the reaction chamber to the turbo pump. It's called the high vacuum valve. So I'm going to open it now like this, and then the pressure will also drop down inside the chamber. Everything went down to crazy low. As soon as I open it, the pressure jumped up instantaneously because it was at higher level first, but then dropped down again. So this is the point where I can continue with my process. I can do evaporation. I can do any deposition like low vacuum deposition, high vac deposition, I should say, sorry. Norfolk, are you guys with me? Were you able to follow so far? Wonderful. Okay, so this just showed you how to carry out a process. So as easy as that. Mechanical switch and mechanical pump. Then we pump down the reaction chamber, close this valve, open the, this would be called the 4-line valve, right? The valve connecting the mechanical pump to the turbo switch. Turbo pump would be the 4-line valve. That will be open up, and then the reaction chamber is at very low pressure too. We are ready to do, say, evaporation at this point. Okay, so things worked out pretty nicely. So I'm gonna stop this program, and then I will run it one more time. Okay, now what I'm gonna try to do is I'm gonna turn on the mechanical switch, and then I will open this valve again between the mechanical and the turbo. Good. But instead of turning on the turbo, I will open this B2, the high vac valve. Okay, so remember, it took us quite a while to lower down the pressure of the reaction chamber over this bypass line. Do you guys remember? It took us really long, like 5 minutes or so. Now it's taking us much quicker. Any guesses why that's the case? See, we're already at the base pressure now. Why can we pressure down the reaction chamber along this line much quicker than this other line here? Any guesses, guys, here on this end?
That's because it doesn't have to go from the reaction chamber all the way down to the pump, or straight down from the chamber to the turbo pump to the mechanical pump.
I mean, geometrically, this is not a great representation of the length of the things, but in a sense, you're right, because the bypass line is very thin, like I was saying, so its conductivity is low. So what do we mean by conductivity? The conductivity of the mass transport of the gas inside is going to be low. It's going to take time. Does that make sense? Whereas look at the turbo pump, the high vac valve, that portion, the radius is large, very large. You guys see that? So it will pump it down very quickly. Okay? But you never do this, okay? You never pump down the chamber just to save a little bit of time over the reaction chamber over the turbo pump. You never do that. Like, you never try to do it over high conductivity, or in other words, larger lines. The main reason is this is a very quick change of pressure. Okay, so this creates a very abrupt change of pressure. Let's say that the vapor pressure, equilibrium pressure is, let's say, I'm making this number up, okay, 20 torrs, okay, 20 torrs. So that's the equilibrium water vapor pressure at 760 torrs, normal pressure. So it has its own partial pressure. If it's higher than 20 torrs that day, it's going to condense. The water would condense, okay? So while you're pumping down your chamber over this large line, you might accidentally pump down things like, you can't control the pump down process. You can pump down the, let's say, some of the partial pressure of other gas much quicker while leaving quite a bit of water there. That makes sense. So this balance, this partial pressure balance will be lost, like 20 torr from the water vapor, 20 torr from another vapor, and the other parts is like oxygen, and that will be lost, because you're going to abruptly take, let's say, all the oxygen from this line while still keeping some of the water vapor here. Okay, so that will make something much higher, because the partial pressure of water vapor will be now much higher than 20 torrs. What's going to happen? it will condense. Does that make sense? Because you have still left 20 pores there, but the overall chamber pressure is lower than 760 because you're taking it very quickly without quickly checking what you're getting out. So in that case, the condensed water will condense on the walls. And that's a very critical thing. You cannot pump down your chamber after a while. With the condensed water on the walls, it will be a killer. It will be very difficult. Okay, so this is not the right way of doing things. So one more thing, let's stop the simulation again. Let's try to understand the crossover pressure of the turbo by trying to almost burn the turbo. Let's do it. So let's, because this is a simulation tool, we can do whatever we want. I turn on the tool one more time, turn on the mechanical switch. Now. So here in this case, if I do that, that would let's open this guy, okay, V2. And I turned on this turbo too, okay? In this case it won't work. It's not supposed to work. Even though it looks like it's working, it's not supposed to be working because it has a lot of load, 760. Turbo blades will not run. But in this simulation it is kind of like working. Okay, now I will open this valve V1 here and I will look at the histogram. So I'll ask you guys to record for me the crossover pressure for the turbo. So I will open this V1 and then let's see the time when this turbo pump starts to take over. Does that make sense? This is going to be the time when the turbo actually works rather than just like tricking us now. So turn on the turbo. Still, it's the mechanical pump doing the whole thing. Because you know, once the turbo takes over, it's going to put it down to 10 to the minus 9. Look at the pressure. Okay, that's it. That's it. That's the point. So this is the point. Like we now know the crossover point. So it's around 1 torr. That's the crossover of the turbo. The turbo actually starts working there. So before that crossover, it doesn't work. It says I'm too loaded. Okay? Yeah, don't make me work. My blades will hurt. By the way, I mean, they can hear us, right? Norfolk, you guys can hear us, right? Yes, okay, okay. That would be funny.
It's a little late for that.
Yes. All right, we have done this too, and what else? There's this nitrogen vents, as you guys can see here. So that's the proper way of venting the chambers over a nitrogen line. Let's say your reaction chamber is now under 10 to the minus 9, right? So I will close this V2, and then I will look at the histogram again, but I will now open this valve. So you see, it's all of a sudden it's vented. So, and then it's going to say vented to atmosphere. I need to be careful because I'm going to start doing CVD. I'm going to start flowing in silane into this, and I should not, of course, vent my chamber when it's filled with silane, right?
Yeah.
That would be a good idea. Okay. Now, what else? We've done the gas flow. Oh no, we haven't done the gas flow. Okay, so now you guys, we were always in this vacuum tap down here. Now I would like you to switch to gas flow. So that's the second tap here. Now all of a sudden I'm seeing the new thing here that says silane reactant gas. So that's how we're going to introduce the gas into our reacting chamber. I will start the simulation again. I'm gonna turn on the mechanical pump. And maybe now we can work on the mass flow controller, MFC, as shown here, and also this throttle valve. Let's do that. So I will prepare my chamber one more time over this valve here. That's the proper way, right? Yeah. Over the bypass valve, you look for the crossover, which was like 1/4 that we found out. I don't need to wait for the whole base pressure anymore because the crossover is the important point for me. And I'm almost there. Do you guys understand that? Well, that's really a high crossover, by the way. Like a lot of the turbo pumps, they don't have a 1/4 crossover. They have like more like 200 millitorrs, 50 millitorrs. That's the crossover that you would see on the tool. So I'm now in the torque range here in the reaction chamber. Yeah, I'm in the minus 10 to the minus range, so I can close this. I mean, I went below the crossover. I'm now opening this valve and preparing this portion here too. It's almost there. It's very easy to pull it down to, of course, because of low volume. And now I'm gonna turn on the turbo, and it immediately brings it down to 10 to the minus 9 as expected. And of course, the next thing will be to open the high back valve to prepare the chamber for the deposition. All right, now, of course, now when I open that up, it makes the chamber pressure 10 to the minus 9. Will any chemistry take place at 10 to the minus 9? Will any plasma be sparked at 10 to the minus 9? No, no, these are too low numbers. So I need to increase the pressure inside the reaction chamber. One way is to work with this additional freedom, additional parameter that's set throttle valve. So you can increase that throttle valve, or decrease it by making actually blocking the passage between the two. So that way you're increasing, you have a chance to increase a little bit maybe. Not at this point maybe, but once after we. So let's set that to 50, okay? Let's set that. I think you can write it on top now. Okay, maybe. Yeah, the exact number is not extremely like 51. That's what I found. All right, now we will either make it a plasma chamber and we will make it a plasma enhanced chemical vapor deposition, or just an LPCVD. So to do that, we need to flow in some gas. We are going to flow in 100 SCCM. But this doesn't really send the gas yet. So enter 100 there and then open this valve here, of course. That is not a valve, that's a mass flow controller, by the way. The mass flow controller, as the name implies, controls how much of gas that you're flowing in. So as soon as I do that, it becomes what? 9 times almost 1/4. No, not 1/4. 1 times 10 to the minus 2, 10 millitorr, right? Yeah. Yeah, so we are in this range now, 10 millitorr range. So if I close the throttle valve, let's see how I have a chance right now to control the pressure change. So I made it 1%, right? So only a little bit of gas is now leaving. I talked about the residence time. So what am I doing right now? I'm increasing the residence time because I don't allow the throttle valve to be open too much. So let's open it again. So you guys see that? So I have the full control over the reaction chamber, over the throttle valve. I can set the pressure to the value that I want. That's one way of controlling things. The other way is, of course, to flow in the right amount. So that's going to be a linear response. So I'm hoping that if you do 10 only, you will see 9.4 times 10 to the minus 4. Let's see. Yeah. So that's going to bring us 1/10 of the pressure that we were aiming for. Okay, now we have learned how to first prepare the chamber vacuum-wise, and now how to prepare the chamber by flowing in the right gas. Now we're going to switch to the third heat transfer tab. Switching to heat transfer. Okay, now it added one more thing, and that's the heating. I will start this tool again. So it allows me to heat the wafer that I put inside to facilitate the chemical reaction, right? That's what we were saying, like in LP CVD. Over a lamp source, this would be the photo-induced chemical wafer deposition. So we will send the light from the mercury lamp, and then this would induce the chemistry. Or we could do substrate heater. Okay, that's more realistic, more common use. Let's make it substrate heater. And this time, I mean, let's take the shortcut and then let's open up the whole thing from here. Okay, like I was saying, this isn't the right way, but we're just trying to make things a little quicker. And then you can turn on the turbo as well. All right, and now let's flow in some gas, like 100. These are nice exercises.
Oh my God.
And we're going to set the substrate heater to some temperature, let's say for 600 degrees. And then we're going to turn that on. The heater will be turned on. This is now going to read out the temperature of the wafer. So we're heating up the temperature, the heater, and then that's heating up the wafer here. Of course, at the expected temperature, we're going to start the recipe. The recipes that I was showing you for the last 1 hour or so. Okay, so we could have done this over the mercury lamp or any different way. The manual adjustment is one other option too. All right, now we're very close. We're very close. Now we're switched to chem reaction. Okay, so that's the last portion. All right, now one more thing has been added to the module. It's not just the heating this time or the gas flow, but the chemical reaction rates too. What we're going to do together is that we're going to try to read out the deposition rates, okay, corresponding to the corresponding temperature and the pressure. So I will give you the recipes in a second. Actually, those should be the same recipes that you will find. I think you guys have this cvd.txt. Okay, yeah, let's look at that. cvd.txt has the recipe. So first, we will do the following. We will increase the temperature, as you can see, and then we will try to, and the pressure is here, 100 SCCM of silane, and we will record the deposition rates. These are the values that I recorded before. They should be exactly the same if everything goes right. Now, going back to the software, you can just follow me. Now, what we're going to do is we're going to do a temperature sweep like we did before. I'm going to try to end up with this graph. Remember, we had this graph, 1 over temperature over growth rate. Okay, so let's do it together, starting the simulation tool, turning on the mechanical pump, turning on this valve, turning on turbo, because I don't care at this point. you guys are familiar with everything, so it's all nice. You can hit this to 100 because we're not gonna set it to something else. So 100 silane SCCM is coming from the master flow controller. I open that up too. The throttle valve is, I guess, open. Yeah, 100% open. All right. Now, under these conditions, first, temperature heating is 25 degrees. That's the first temperature we're going to look into. And I will turn on the temperature heating. Wait for it. Let's just switch to manual adjustment, or set it to manual adjustment. That's the easiest one. Instead of waiting for temperature increments, we'll just set 25 degrees. And then we'll keep an eye on the film thickness, the deposition rates here, okay? So what does it say? 6.3 times 10 to the minus 16. You guys see that? That is a very low number, right?
I got 2.5 to a negative 17.
What's yours?
2.5 to the negative 17.
Okay, that's also cool. I don't know what's different, but okay. Yeah, there might be small changes, but you guys must see something like as small as this, very, very small. By the way, I think my number was like yours too before. I don't know why it switched a little bit differently. Yeah, 2.5 times 10 to the minus 17, right? Okay, now we are going to switch to 50 degrees. What we're going to do is set to 50. And we're going to observe the deposition rate change or not change. Doesn't really change. What does this mean? The 50 degrees is not enough to facilitate the reaction. Does that make sense? We are not growing any thin film yet. We're not growing any silicon yet. So switch to 100 degrees. Of course, the proper way of doing this would be to write down the numbers too, right? So you would like to write down these numbers to a piece of paper or to your notebook. But don't worry now because I have it written for you, okay? So you just to speed things up, you don't have to worry about that part. We will just use those text files that I sent you. All right, now at 100 degrees, we're giving in some heat. That is like activating a little bit of chemistry. So it's not it's not the same identical number, I remember. It's a little better. What do you guys read? Joshua, what do you guys read? 6, you read 6, yours, Joshua? Yeah.
I got 2.5.
Yeah, oh, that's fine. Still 10 to the minus 17.
Oh, yeah.
Okay. Now, switching to 150 degrees. Okay, so now we start seeing something at least. 150 degrees gives us some improvement from 10 to the minus 16 range. So in the logarithmic scale, it's going to follow as a linear plot, hopefully. Now, one more step, 175, because now we're starting to talk a little bit. 200 degrees gives us to 10 to the minus 10 range. To 25, 10 to the minus 9. These are still very, very little. I mean, I'm not really growing anything. Okay, so let's do something real because, I mean, it's going to take quite a while to get these temperature readings. Norfolk, do you guys see what I'm doing now? I'm getting these points from this plot, and I'm hoping that I will end up with a similar plot for the overall CVD. I have like several sampling points from the temperature, corresponding temperatures, and I am now calculating I'm getting the reading out the deposition rate, corresponding deposition rate. Now let's switch to 500 degrees. Okay. Yeah, what do you guys read? Is that the same on your screen?
3.0.
Yeah, yeah, 3 times 10 to the minus 2 nanometer per second. It's still low, so 500 degrees is still low, but I'm starting to grow something. Let's go to 800, and then you guys will see what I mean. Okay, so this is a good deposition. It's a very good deposition value. It is 1.6 times 10 to the minus 1. So that means 1.6 angstrom per second. It's a very good deposition rate. Even though it may sound ridiculously small, it's I'm accustomed to these kind of values. All right, 1.6 angstrom. Now, we have seen this linear change, hopefully. I've shown you this linear change. You have sensed the linear change. Now switch to from 700 to, pardon me, 800 to 700. What happened? Big difference, Joshua? Nothing happened, because what happened? Well, I got a point from here and I got a point from there. Now I'm giving the temperature, but the system is diffusion limited. So it's saying that whatever you do, I'm not going to move. All right? So it's at 700. Let's do the following. So come here, give a little bit of gas. Instead of 100, let's say 150, and then let's observe the deposition rate change. Okay, it did jump, right? So what happened? I gave a little bit of more gas, so it's it did elevate its because I am now presenting more gas. It did elevate its the deposition rate a little bit. Okay. Now we will stop the simulation because we have a lot of points that we looked into. Now we will go to MATLAB. So I gave you guys this, first let me see, by the way, CVD1 and CVD2, two text files. I'm looking into CVD1 right now, 25. Yeah, these are the temperature values that we scanned. You can do the same for now on your MATLAB. And the third column is the pressure. The second column is the deposition rate. The first column is the temperature. We're going to read this together. I mean, not read it loud, but make MATLAB read this text file. So we're going to do the following. Everyone, you guys can write your name. Oscar is equivalent to, okay, DLM, read. Delimiter reads. Just, you can write your name here first. That's going to be the file that's assigned to the what we call the matrix that it's going to be assigned to. And we're going to read this in the corresponding way. We're going to put an what's this called? Apostrophe. So put one of those, okay, to see what I did put. And then you will have to write down the name of the file that you will read it from. CVD1, CVD underscore 1.txt. Okay. Your name, yeah. Emil is equal to. And put the next apostrophe, and at the end put your parentheses, and then put this one. What's this? Semicolon? No?
Yeah, that's a
Semicolon, yeah. Semicolon, yes. And then you can hit enter. Okay, you guys have all hopefully done it right. And then it's going to put this whole thing into your workspace here. Okay, this is me out.
I did that like
Yeah, but
You see, I don't have. I don't have
it kicked me out of the.
that. Or that.
Did you? Okay.
I'm back. This one kicked me out of the server for a second.
After I hit enter, what happens? You got
I didn't get the area.
Yeah.
21 by 2.
Yes. So on the workspace, at the left bottom corner, for Penn State people here, on your case, wherever your workspace is located, it might be in different areas. Okay. So we're gonna plot this now. This is now coded into your little matrix. If you double click on it, it will open up this matrix here, and that's the identical thing that it read it from this text file. Okay. What we're gonna do is we're gonna plot it. We're gonna say plot. Paula, did yours?
Let me try.
Okay. Okay. We're gonna say plot. Oscar, your name right now, whichever matrix is yours, and then we're gonna put another parenthesis to say that we will plot. This is gonna be my x. Okay, this is gonna be my x. X is the first column, right? So it's the first column of Oscar array. Sorry, matrix Oscar. So I'm telling it like that. Plot Oscar. Now what is this one called? This
A colon.
colon. Yes.
Colon, comma, 1.
Colon, comma 1. And then this is your x. How about your y? Your y will be the other one. So you can guess how I'm gonna write it down. Oscar, colon, comma 2. But we won't stop there because I think we need to plot it in the logarithmic scale. Let me see. Yes, so we need to plot this in logarithmic scale. Go to logarithmic 10. Log 10.
It gotta be logarithmic, so it's gonna be log,
Log
10,
10, yes.
your name, open parentheses,
Exactly. Log 10,
colon.
parentheses, and another parenthesis. So you should put Oscar into the parentheses, or your name into parentheses, your matrix.
I'm just typing in log 10.
Yes, just type in log 10 and then put 2 parentheses before and after. Okay?
Okay.
Like before and after. But we need to plot it correctly because it's 1 over T, 1 over temperature. So, and then the temperature is always given in Kelvin, okay? So we need to first change this to Kelvin. Let me start from beginning because it's gonna be too complicated. So going back, Oscar, this is the first X. I'm gonna add 233 and I'm gonna make it a Kelvin, all right? And put this into little parentheses, okay? And then next, I have to plot not this, but 1 over this value because I'm plotting 1 over temperature. So put 1 over 1 divided by this. Before the divided thing, put a little dot, okay? Put a little dot before the divided division. Okay, so this is my x. Now, I'm gonna plot, like I said, the logarithmic 10 of my matrix. I put log 10 and I put my matrix into little parentheses on both sides. Did you guys do that? And MATLAB actually gives you a great chance to check your parentheses. Let's say this is the first Oscar parenthesis. The second one is the logarithmic parenthesis. The third one is the main plot parenthesis. And then at that point, you can hit enter.
Click.
I'm down to unexpected.
Want me to check it? With
Let me see. Hold on. Let's see. It's
open.
one open, two open, three open, one, two. We have one more than we.
What happened, I know?
Open parentheses 1 point.
Yeah, so the number of parentheses may be a bottleneck. Let me check quickly.
I think they just one extra.
Yeah, let me see.
Interesting.
I don't have to see.
Oh, neither do I.
So you don't have CD one?
I didn't download the whole thing. I just downloaded the papers. I just downloaded some sheets.
This one, this one.
I don't have it.
There's a parenthesis missing here, just before ML. You can just go to ML,
Oh.
because you need to convert that to Kelvin, right? Exactly. And then that looks,
There's one of these.
there's one more. Yes, now in enter.
Oh, I have it.
Yes.
Okay.
So you guys hopefully can also see on your screen what we were talking about. We were getting measurements 1 over temperature in Kelvin, and this would be my growth rate. In terms of what? Nanometer over second. Okay? So this part was all linearly changing in terms of logarithmic scale, of course. This would be my kinetically controlled. So my chemistry dominant part would be this part. Does that make sense now? Better? This is the chemistry controlled part. As I was changing to elevating the temperature, I was seeing some changes on the deposition rate, right? That meant that it was the chemistry controlling this. On this case here, I see that it's getting saturated, so that is the diffusion controlled part. I can alter that part a lot with my temperature changing increments. Okay. So that's good. Now let's do one more thing. We're going to try to attain another plot. That's going to be the CVD2 plot, CVD2.txt. In this case, we're going to fix the temperature. As you can see, it's going to be 600 degrees. We're going to increase the pressure, and then we're going to start to record the growth rate accordingly. All right. Now, coming back to this simulation program, I'm going to turn on the whole thing one more time. Mechanical switch, turbo pump.
Oh, yes.
Everything is turned on. Great. So now everything is set to 600 degrees. I can turn that on as well. So temperature 600 degrees. Mechanical pump is turned on. This valve is turned on. Turbo is turned on. I will scan for the pressure change. Now, first, how much should we flow? That's a good question. Well, let's start from small numbers, like 1 SCCM. Let's see what that will bring. Okay, so I'm giving only 1 SCCM, and then it's bringing me 1.6 times 10 to the minus 3. You guys see that? It's here. So it's happening because I have enough temperature here. As soon as I introduce even a little bit of this, I'm getting some deposition rate. But it's diffusion controlled because it's not getting enough of this, and it's not saturating. So what I mean is, if I were to increase the temperature still to 700, I don't think it would change drastically. Yeah, it didn't change even if I increase it to 700, as you can see. So it needs more pressure. Let's give 10 SCCM, and then it jumps to 1.5 times 10 to the minus 2, as you can see. And then we can flow in more and more. So 50 would give us 7.3 10 to the minus 3. So see what's happening. Film thickness is increasing. So we are growing thin film. 1 nanometer has been grown. So once we enter 100 SCCM, now it's 2 nanometers. We have a growth rate of 1.4 times 10 to the minus 1. It really gradually increased. Now let's see if I can put this into some saturation as well. So I will do the following. I will increase this to what? 1000. Yeah, 1000 is giving me this. Maybe I need to increase it even more. So this is really now very high, but not extremely high either. Because see, it's only 6.8, no, 68 millitorrs. So that's still not very high. If I add one more, that's going to make it 72, no, 0.72 torrs. So these are large numbers. I end up with 1.1, okay? So if I add one more zero just for the sake of doing it, I don't increase it. You guys see that? So it's getting stuck. I have increased it very much. It's almost close to the venting 760, you see? But it's stuck. What does that mean? Now I'm working it into the chemistry dominated region because I'm supplying too much of gas, but it's not increasing the deposition rate. So I started like this, and then all of a sudden I saturated and I stayed there. So let's try to plot this one as well. Now going to MATLAB, we have to read CVD2X. The easiest way is to do the following. So write down the same like Oscar here, and then hit the up arrow. That will bring this from its memory. Okay, Oscar is equal to PLM read CVD1.txt. Now we will say Oscar 2. You can change it in any way you like. And then we will say CVD2.txt. And we can now hit enter. Now it's added up another one here. This is now the Oscar 2 matrix. It has more entries, as you can see. It has 43 rows and 3 columns. Now we're gonna plot this matrix here. How are we gonna plot that? The same ways, but let me check the axis. So we're trying to plot it for torr versus nanometer per second. So the units are okay. So what I'm going to do is hit plot again, click PL, and then hit up arrow. It will bring it the same thing from memory. You guys are with me?
How did you do that? Up there?
PL, and then hit up arrow, so it will bring it from memory. The same plot command that we used before.
Oh.
Now, we will do the following. We will, instead of all this, now we will use the second column, no, the third column, sorry, that's the pressure column. So Oscar column comma 3 is going to be our X. On the other hand, the other Y will be again the second column, but it's not logarithmic scale right now. Yeah. So drop down logarithmic scale. Log 10 is done. Don't forget the extra parentheses that we put it for that. And it's easy as that. Now, Oscar 3, Oscar 2. One of them is X, one of them is Y. So here we can hit enter once you guys are also ready. Uh-oh. That's not right.
Didn't you have to put over 2? Or not necessarily?
No, that's the deposition rate. We're interested in now. Let me see this portion, the third column. That's good. Let me see. That's partial. I'm not sure. Let's try it again. Oh yeah. Sorry guys. So this is Oscar 2, right? Oscar 2. That's what you meant, right? Yeah, sorry about that. So this has to be your second matrix, of course. Yes, and then you end up with this. You should end up with this. This is, of course, the growth rate, nanometer per second, y-axis, and x-axis is what? What was the x-axis again, guys? Pressure. We're flowing in different levels of silane into the chamber. What's happening? Well, initially, we are adsorption limited, so we don't have particles so much yet. So it's diffusion limited. Later on, it becomes chemically reactive limited. So here, it becomes chem limited. Even though we offer more silane, it does not react quickly. Here, we offer silane and it reacts immediately. So this is the diffusion limited portion. So what we're doing is actually going back to the lecture slides, these two graphs. We have just created these two graphs. Yes, so first one was, of course, this one. We have seen that, logarithmic scale of growth, and with respect to 1 over temperature. The other one is this one. So we are absorption limited here. They offer more silane, and it does go into reaction easily and nicely. We offer more, but it gets saturated because it becomes surface growth limited or chemistry limited on the surface. So we have established these two. Any questions on your side, Norfolk? Were you able to follow, plot the same graphs with me? So
No, like small.
You're zoomed out.
yeah, you guys nicely seen that, yes. All right, now we can close this software. The kicks in if it's open. Let's see. See, we have in all that time we have deposited 560 nanometer.
Yeah.
But our flow of the silane is enormous. That's very high. As I was saying, turn off the heater, turn off the mass flow controller, of course. Now, you have to wait because there's been too many reactions here. You have to be very careful. The turbo should take over and then we'll pull it down. And there's going to be even a more waiting period here. What's happening? All that silane and all those byproducts will be going to the exhaust, to the scrubber or something like that that I was saying. Because you can't take your samples out yet. Your hands would also get burned because it's very quick, 600 degrees. So you have to vent it pretty timely. But at this end, I mean, at some point, of course, you will close this high vac valve here. and then you will be ready to vent the chamber to take your sample. Those professional facilities are left like this while the turbo is still working, okay? A lot of the time, they don't turn off the turbo. You guys don't have a chance to play with the turbo because they're rich and they can just replace their turbo pumps every 2 years or so. So they don't turn off their turbos. It eats away their the lifetime of the turbo pump.
I said, we got that rich, basically.
All right.
So maybe next one then?
Maybe next time. All right. Now, I will quickly go into the ALD and let's see how much I can do before the time. It's really going to be a little smaller portion of CVD. It's like sister or the brother of CVD, and this is going to be your project, as I was emphasizing. So now, this is my famous, not famous, my favorite, my most favorite deposition system, and I love ALD. Okay, and I hope I will show you why I love ALD. Okay. So remember the problem, the conformality problem, deposition problem. So for those different deposition methods, we were not able to get a conformal coating like this. The sidewalls would not be coated at the same rates, right? We wouldn't have that. And I told you one more thing, that this was the research problem that I was working on. So I was trying to deposit on this whole little nano post here with silver. But as you can see, I wasn't very successful in coating some portions. Now, at that point, the student that I was working with switched to ALD, okay? My boss told him to switch to ALD. And look at the response. It nicely coated very well over that, yes, over that step. So ALD will give you a super nice control and you will just admire it. Okay, so it's very similar to CVD, but this time the precursor gas that we will flow in will be sent alone, and it will make more sense as we move along. So it was initiated in 1974, as early as that. It's not an early, a new recent innovation or anything. It was there, but people found it to be too time consuming, so they did not pursue ALD all of a sudden. Okay, so this is how ALD works. You send the precursor one at a time, and then like send the precursor one. Okay, this is your substrate, initial substrate one. You send the precursor, you let the precursor do its some chemistry on the top, and then you purge the whatever you have inside in the third cycle. And then in step 3 here, you send the second precursor. So that's number 4. The second one flows in and does more chemistry here, and that's what you end up with. Okay, so this way you have a chance to grow like very nice coatings like A, B, this kind of very controlled coatings, because everything is going to be done on the surface and you have a chance to deposit one atomic layer at a time. You guys see that? You have a chance to deposit one atomic layer at a time. Okay, that is super important. Remember our earlier, the PECVD and sputtering evaporation. There was no way to deposit one atomic layer at a time. This is now extremely nicely controlled. If you like to deposit 8 layers, say 8 individual atom thick, you can do that. That's as controlled as it is, as this can get. Okay, so it's very similar, as you can see, to CVD methods. You have a furnace kind of thing, like a heater that will increase the temperature and enable the chemistry. You will send the material from these two precursors, as you can see. They should be very reactive. And then they start the reaction, but you send each precursor one at a time, single. You don't send them at the same time, unlike CVD. They don't react. You send one of them and you let it react with the surface and then let it get exhausted outside of the furnace. Does that make sense? And only when you make sure that it's all gone, you send the other layer, other precursor. That's the main difference. So let's look at the deposition of alumina, which is aluminum oxide, Al2O3, okay, on a silicon substrate. This is exactly what you guys would do. So you have silicon substrate, and all the time silicon is going to be terminated with these hydroxyl groups that we call silanols, okay? As it's sitting on the lab, the humidity will make sure it will be terminated like that. So you have oxygen and you have hydrogen, all right? So that's what you will start with. This is a non-ideality, but this is going to be handy in this case. So you will introduce one cursor that is going to be TMA, okay? Trimetal aluminum. So that's this. See, it has these 3 bonds, each going to 1 carbon, and then that carbon has also these 3 hydrogen. So it's very close to creating methane gas. You guys see that, CH4? It's very close, but it's not there yet. So it needs 1 more hydrogen to do that. And do you guys have any guess where it can capture that hydrogen from? Right, it will capture the hydrogen that's seeking from this surface, from the silanol. And that will release the methane gas like that. All right. So that's exactly what happened, as you can see. It did capture that hydrogen, CH4 became more stable and got exhaust, going to the exhaust as a byproduct. Methane has been released. What did we do? We have achieved aluminum to oxygen bonding. That's good. What will be the next step? So we released the first precursor. Notice that I'm not releasing the 2 precursors at the same time. This was the first precursor. Now I have to make sure that all these bonds are completely attached, right? How can I do that? Well, I just give a quick pulse of TMA, trimetal aluminum, okay? If I give like some hundreds or tens of milliseconds waiting period, it's gonna find every bond on the surface, okay? So it's gonna go and search for every bond on your silicon surface. Does that make sense? So even if the wafer is top down, flipped down, okay, it will go down underneath the wafer and it will try to find the bond. If it finds the bond, it will form the bond. So all of this will be formed. And still TMA is coming up. Do you think it will be doing any reaction? No. This is what we will call surface limited kinetics. So all of the bonds on the surface now will be tied up. So we do not have any available bonds. And it will be, again, yes, just like CVD, it will be chemistry limited. But this time, it's not about like a chemistry kinetic limitation. It's actually the whole surface has been covered with one atomic layer of aluminum. I mean, in this case, TMA. Okay, we don't have any bonds available. So we need to get rid of these. Okay, so first, since methane will be released, you will see that this pulse will be enlarged because now there's going to be a detected methane gas release in your gauge. Does that make sense? So it will not be a sharp pulse on your gauge reading. It will be a lengthier pulse. Okay, now, in the next round, you send your next precursor, that's going to be water vapor, only after making sure that you purge the old rest, unused TMA away, okay? Makes sense? They all go away, you wait, you purge them away, purge. You have to wait. Like this can take up to 10 seconds or so, easily. Later on, you send your second precursor, water. And the water will now, okay, so I have CH3 here, and I have some hydrogen bonds here. So there's going to be another interaction between the two, and another methane gas will be formed, CH4, right? From the water to the carbon, the CH4 will be formed, and then I will have another methane released. So that's going to breach this time water will lose the hydrogen, but it will open up the aluminum. Do you guys see that? And then I will release the methane like this, and it will release double the amount of methane, because remember, now I have double methane here, right? Does that make sense too? Right. Yeah, and I started to create my aluminum oxide already. So see, aluminum oxide, it's layer by layer getting created on the surface. So what's going to be the end result? Once I purge the unused water vapor away, together with the methane gas that's been created as a byproduct, I purge them away, I end up with this. I have again hydroxyl group on the top. This is exactly like how I started. Does that make sense? I started to ground level 01, or ground level 0. So now I'm going to send again TMA. It's like a for loop. And that will add up the whole thing, and I will have a super nice control over the whole surface aluminum oxide that I will create. So this is becoming a really new and I mean a very hot topic again, ALD, atomic layer deposition, and people are starting to work on, like you guys will do, oxides, gate oxides of the transistors will be created out of these like alumina with ALD. So your research will be about like those trapped charged particles inside the alumina. Okay, you will compare the concentration of these like charged particles and these defects, like these. Let's say this oxidation was not completely done. Okay, so that's going to create a defect. You're going to electrically and optically characterize that with respect to a thermal oxides, oxide that's grown in a furnace. Okay, so we will send pulses, of course, like first pulse and the second pulse of the precursor. The first one will be the TMA, the second one will be the water. So once you look at the histogram, it's going to look like this, okay? So that's why I was saying it's not going to look like a very sharp pulse like that, but because of the methane release, it's going to have a long tail, because the methane will be released, and then that's going to add some increment to the overall gas detection. You can really count those little pulse cycles, and that will give you the number of aluminum oxide, aluminum layers that you have grown. Well, it's a very slow process comparatively, but because you're growing layer by layer, atomic layer by layer, but you can do this at very low temperature, and it has a super nice control, because you know, once you have covered the whole surface, you're done. That is it. I mean, and then it will give you a very nice conformality like I will show you guys. The difference, main difference is you have now made sure that you don't have like these gas-phase reaction, because you don't send the gas, the two precursors as in the case of CVD at the same time. Does that make sense? You're not allowing them to go at the same time. You don't need high temperature as well. You will get excellent film quality at cold temperature. And these are just details, but by the way, you can also facilitate plasma too in ALD. So now researchers, I will take you to the clean room, and then you will see that there's a plasma enhanced ALD as well. Why? Because you need to improve the throughput. You need to increase the kinetics of the reaction. It's too slow, layer by layer, atomic layer by layer. And plasma will give that kind of facilitate that reaction faster, if that makes sense. So that you don't have to wait for too long to have this whole surface covered, for example, something like that. In the end, results will be like this. Beautiful results with the same thickness all around, like whatever you set it to, everywhere it will have the same thickness. Look at this cross section. It's almost impossible to do this with other methods. And they have done the following. They have tried to coat hafnium oxide. That's another oxide you guys might work on. I'm not sure what Osama will say, but you guys might also work on that too. So they have done a marathon test. They have coated 2,000 wafers, okay, 2,000 wafers with hafnium oxide. And this is now showing you the total number of wafers. Yeah, 2,000 wafers has been reached. And they're looking at the film thickness, okay? Film thickness variation, uniformity problem. Do you see that? So are they ending up with different thicknesses or not? At the end of the 2,000 wafers, they have ended up with almost the same thickness here. What is the thickness? Around 20 angstroms, 2 nanometers all the time, almost every time. Why? Because it's a very controlled process. Do you see that? Well, I did this experiment with you guys. We took pictures of an ALD grown aluminum oxide, right? And then we've seen that we aim for 10 nanometers, right? What did we end up with in the ellipsometer measurements? We ended up with 10.7. 10.7, and we took different measurements all around across the wafer. The smallest one was like 10.51. What does that make? That's make a difference like 0.2 nanometers, right? That's very small. All right, 2 angstrom difference. Whereas we grew a thermal oxide in our furnace, and these are like the changes. Like we have seen like 129, that's like 130 nanometers, up to 150 nanometers. So we can see a growth rate change on the surface of the wafer. We have like 20 nanometer of a change already there, right? That's really large on the same wafer. You don't have the same, this is the uniformity. So we have like a large, this is thicker, much thicker in here, much thinner in there. So it's like almost like little stairs. Yeah, here going down the. So how many minutes? Yeah, we still have half an hour. I think we'll be able to do it. I won't even take that much of time, but we will work on the last MATLAB code that I gave you guys. So here's what we're gonna do. This is an aluminum oxide grown by my colleague, and he's looking also into the, you see he grew it over a shadow mask, so he only grew the aluminum oxide here, like these, through these, okay? And he puts 2 electrodes and he looks at the resistance that he needs. He can extract the resistivity Why? Because resistance is equal to resistivity rho L over A. If you know the area and the length and the width, the area, width, and the thickness here of the sample, you can extract the resistivity too. Why is it important? Because you like to characterize the deposition, okay? So you guys won't do a similar experiment like this simple state, because that's too simple and crude, but you will do similar things too. And he looked at the transmission. Look, AZO, aluminum zinc oxide, that's what he coded. When you look at the wavelengths, different wavelengths, AZO filters out like close to 10% of the lights. That should not be very surprising for you, because where do you use aluminum zinc oxide? Where do you use zinc? Not maybe AZO, aluminum zinc oxide. Where do you guys use zinc?
Roofing.
Huh?
Roofing.
Roofing? Maybe, I'm not aware of
That's
that.
like coins.
Coins. Yeah, there's cleaners. Where would you use that so that it will become healthier for you, the whole sun?
Oh, sunscreen?
Yes, you use a little bit of zinc in the sunscreen so that once you go into look at the UV range, it drastically lowers it down from here to here, right? So it absorbs, so it doesn't let your skin to interact that much. So we will do the following. We will start with a silicon wafer, okay? And as I was saying, this is an ellipsometer, and maybe you guys already did a measurement with it in your Norfolk too. This is a laser here. We're sending the light from the left, and this is our photodetector, PD. The material reflects back the light, and then you try to extract the information from the photodetector. So you try to extract what information? The thickness. So we will just get a silicon wafer, an ordinary silicon wafer. The steps will be the following. We will have a certain oxide grown, a native oxide grown on our silicon wafer, okay? So that's unavoidably happening, silicon dioxide growth. Later on, we will put it in the ALD, okay? And then we will intentionally grow this time some aluminum oxide. And then we'll take it back. So we will this time have an aluminum oxide grown on the top, as well as a native silicon dioxide. So we'll have a sandwich silicon dioxide, and we'll try to figure out the thickness of each layer, okay? Like we did in the lab. You guys remember the experiment? We did the first experiment of the ellipsometer measurement before we do the atomic layer deposition with the ellipsometer, and then we do another ellipsometer measurement at the end to figure out the thickness of the aluminum oxide. All right, but first we need to understand what kind of a sample we're looking at. We have air. We're sending the light with an angle theta of phi, and then we'll get some reflection. So going back to MATLAB. Let's close these guys, and you can close all that CVD1, CVD2. Make sure that you have silicon.txt under the same folder with ellipsometer 1, 2, and 3. Okay, those are the things that we will use. All right, so this is the first thing we're trying to achieve. I will show you illustratively ALD. By the way,
Silicon that what is it?
si.txt. You don't have it there?
Was it in the same folder as anything else?
Did I forget to? So you guys don't have it now? I forgot to give you. Anyways, so you can just watch what I'm doing. Don't worry. Don't worry. All right. So before going to the atomic layer deposition, of course, you need to prepare your substrate. So Rene has uploaded some videos for you guys to watch. Okay, just watch the videos. This is gonna walk you through the whole atomic layer deposition of the AZO, aluminum zinc oxide, that we are gonna cover. Just to give you a brief, quick look. Can you hear the voice too of the video? Yeah. So this is the tool, and believe in me or not, this tool will cost like quite a bit. So these aluminum ALDs are really pricey tools. So you load your sample into the substrate heater, onto your substrate heater, and then you give your recipe to the tool. This is the recipe for the purge time, or the time to actually flow in the gas and to extract the gas, the outcome, the byproducts out. So you enter all of them. The resolution is a little low, but okay, so that's the important thing. You start to see these peaks. I hope you can see them. So they will show you how the ALD is carrying out the whole process. It's sending one precursor, and then purging it, and then sending the next precursor, like following these peaks. I think this video will clearly show you what I mean by this whole presentation that I did before. Okay, now, let's say that we go to the lab, and we would like to get just one ordinary silicon wafer, but we would like to also understand what kind of a wafer we're looking at. Is it silicon or not? To understand that, we need to run ellipsometer1.m, okay? That's the first one we will run. Ellipsometer1.m. Double click on it. Yeah, it won't work with you guys because you don't have that silicon. I'm talking to the folks here. Forgot to give them the silicon.txt. So ellipsometer1.m ellipsometer can also be used to find out what kind of a substrate we're looking at. It's an optical measurement, and once you hit run here, okay, so it's going to ask you, this is the range where we send the light, 0.3 micrometers to 0.8 micrometers. We'd like to understand what kind of substrate we're working with. Enter the incidence angle in degrees. So I'm going to enter 70 degrees. So those are the common incident angles for the ellipsometry. So once I send 70 degrees, I hope you guys also obtain this. The photodetector, the laser sends the light, and from the substrate, I get the light back to the photodetector. This is the laser. By working out at the end, doing reverse engineering for an incident angle of 70 degrees, I try to understand what am I looking at, okay? If I'm really looking at the pure silicon, like in the case here, it should follow the same lines here, okay? These are the silicon parameters. And this is exactly what's happening. So I'm trying to tell you that ellipsometer is a good tool to get good optical measurements in terms of reflection, but that can also tell you what kind of a sample you're looking at. So this is the ellipsometer data, and this is the material data that you can find over the web. So they're coinciding perfectly. This first proves you that you're looking at silicon. That's good. You established what kind of substrate you're examining, okay? Now we start with the silicon. The second thing we will do is we have now of course, a non-ideal case, and as the silicon wafer is sitting inside the lab, it will grow a native oxide. What's the usual thickness of an oxide? It's very thin, right? It's going to be a native oxide, so it's going to be only a few nanometers most of the time. But in this case, this is like beyond being a native oxide. So this is a little, okay, so this is going to, okay, can you guys see me? So this is a little thicker than usual. Okay, so we have like a thickness of an oxide here right now that I'm trying to figure out with, again, ellipsometer with some angle, incident angle. You guys will use the software that I gave you again, so work on that again, so don't worry. I'm trying to understand how much of a thickness I have, so we will use ellipsometer too. These are the measurements. The measurements say that at 50 degrees, I have these two measurements. The measurements themselves, the physical sense, is not very critical for us. I mean, it will take me a while to explain them, but it's not important. Just assume as if you're just noting down as an engineer in the lab the measurements that you see on the ellipsometer's monitor, okay? These two measurements, phi and delta, or psi and delta. Okay, now going to ellipsometer 2. Okay, and running the code again. Now this is asking me, enter a guess thickness in angstrom. This is what you would do if you were doing ellipsometry most of the time. You have to guess the thickness of your oxide. And like in our case, there's a tool in our lab, and you have to start by guessing the thickness of the tool. So I'm just going to guess 100 angstrom, okay? 100 angstrom. Enter the incident angle. So I'm going to say 70 degrees again. All right. And my ellipsometry captures the information only at this given wavelength. Okay, so it only measures it at a specific red laser wavelength, okay? Because it only sends this particular light, wavelength light. So I'm going to enter, you guys can do the same, 632. Now it's going to become like a number game, because I hope you can see these two numbers here. These are the measurements now the ellipsometry would expect. So it's what it's telling me is the following. If you're doing a 70-degree incidence angle, you will see that psi will be 11.49, and delta will be, delta is here, at 7 degrees again, 28.01. Okay, let's just keep them there. And let's return back to our experimental results. Our experiment, on the other case, says that our for 50 degrees, my psi is supposed to be 3304, and my delta is supposed to be 81.4. Okay, so I'm pretty not close. I'm not close at all. So I wish we had like a half an hour for you guys to work this around and see how the ellipsometer works by guessing the correct thickness, okay? But I will guide you now because we don't have that much time. So the aim is to, because I just guessed a thickness, 100 nanometers, right? So I'm going to guess a different thickness in the second time to make sure that I will get something closer, or I guess probably not 110 nanometers. I will get these two numbers closer. So as soon as I am getting closer to them, that's going to be actually my real thickness, the thickness of the silicon dioxide that I'm looking for. Okay, let's go back to ellipsometer 2 one more time, and let's run it again. This time, instead of 100, let's say 500. I think I said 100, right?
You guessed it was the first time.
Yeah, you can check it from the memory too. It's 100. It has a wonderful memory, unlike I have. So I will say 500 and then hit enter. So I'm going to stay the same, 70 degrees. And I will look at the same 632 nanometer laser wavelength. So yeah, okay. So this is now getting closer, 22.81 and 84, the other one. So, okay, at least like much closer to what I'm expecting. All right. You guys see what I mean? So this was our initial value that we found. So ellipsometer is working very close to what we are having here. So it's going to make sure that the value that I will have read here, it will be the exact value that I'm supposed to get. So I need to guess another time. Instead of 500, I'm running it again. I'm going to say, I think it was 800 something. So 800 and 7 degrees, 632. Yes, so you see 800 gives me almost this number that I'm looking for. That's what I meant by guessing game. So it says psi is 32.5 and delta is 81.73. Almost the same, right, guys? So I'm in the range. So I think it was 810. So I'm going to say 810 now, and 7 degrees again, and 632. Yeah, almost. I mean, yes. This is the almost the right number. Or I think it was 814 or so, something like that. So if we had time, we would like 100% find it. Actually, I have like this shortcuts teacher code that helps me to run it for all range. Okay. Regardless of, so you guys, I don't think I gave you this, but it's not critical. So what does this do is it scans for the whole thickness range and it tries to find out the corresponding. So instead of guessing, it does a little bit more computation, as you can see, right? We are waiting, but in the end, it gives me the final result, the thickness that I'm looking for. Hmm?
So you put 1,000 H.
Right. Gonna get finalized soon. So whenever you see like a busy writing here at the corner from MATLAB, it's doing a for loop, doing some looping. That's why it's wasting time. And pretty soon it will be done. No.
Oh, no,
Well, the busy writing should go away. Okay, now in the next round after this, I'm very close. I think it's 810 or 814. So the next thing will be, I will have now done an ALD coating of aluminum oxide. So now I have to figure out the thickness of this aluminum oxide, but I have to know the initial silicon dioxide to do that. So I will enter my initially found silicon dioxide thickness to end up with the aluminum oxide thickness in the end. And these are the measurements for the combined, the sandwich case here. Okay, still running. Okay, yeah, so this is the teacher code because it shows us without any estimation or guessing for the corresponding thickness. We're looking for these two, right? So I'm gonna just take this thing and I'm gonna go into this range here. And I'm looking for 32, 3304. Yeah, that's the right one. So like I said, 814. So my oxide thickness was 813 angstrom, so 81.4 nanometers. It's just a coincidence that the delta is the same number, okay? There's nothing really right. Okay, so in the next round, I'm gonna do the same. Let's run it with the feature code again. So this time, as it's saying, enter the initial silicon dioxide thickness. I will enter my initial 814, and then I will guess something, but it doesn't matter. It's just going to find it out. And 70 degrees is the incident angle. It's going to run one last time. And then we're going to try to find out thickness. I think it was like 910 something or so. Okay, in the end, as I was emphasizing, ALD gives you the ultimate control, and you can see the control thanks to ellipsometer measurements like this. It will be able to measure to the angstrom level, okay? So you will definitely tell the thickness of a layer at the angstrom level. So that's very critical. So again, looking at my numbers, let me write them down. At 7 degrees for aluminum oxide now, it's 27.41 and minus 77.72. That's my expectation. Well, I'm going to take 1 more minute or so, and then the result of chemistry. Yeah, that's why this whole controlled deposition is the main reason why I love ALD, and we'll be working on that together with some of your friends here over the summer too. Yeah. And tomorrow we will talk about nano imprinting. By the way, while we're waiting, I'd like to share with you one last remark. As I said last week, please do not forget to take a look at the Wednesday self-assembly and block copolymer, these 2 virtual labs. Please go into them. The Wednesday, underneath Wednesday, you will see them, these 2 virtual labs. I do not think that it will take more than 2.5 hours or so, okay? So it will be very, very easy. And please solve them, because we will have like a, I don't know, half an hour discussion or so on Wednesday morning. It will be very quick, so we can contribute all together. And tomorrow afternoon, you guys will watch these 2 after talking about nano imprinting. UV nano imprinting lithography and micro contact printing lithography. You'll be doing these 2 labs by yourself. So you guys can do that in your dorms, the folks here. But you guys will do it there with your teaching assistants in the afternoon session, okay? So that's the plan. And this guy is still working on this. Question? Yeah, I'm checking the chat window. I think it's going to take a little while, but I think the result will be, if I remember right, 900 and something. Yes, you guys can take the quiz. Yes, yes, that will be great actually, because that will give you a chance to really weigh where you are, right? Yeah. So we can look at the answers and we can discuss all together. So, but again, those grades will not be critical for you, okay? So don't put any pressure on your shoulders. We're not monitoring anything. It's just for your own learning experience. Does that make sense? So please take the quiz if you like, because that's going to tell you how much you know, how much you learn more realistically in a real-time quiz. When is the deadline? Well, you can take it anytime, actually. There's no real deadline. But if you do the Wednesday ones like today or tomorrow before Wednesday morning, because on Wednesday morning we will discuss those 2, okay? Does that make sense? So again, we will discuss those two, what copolymer and self-assembly. So I'm hoping that you guys will have a chance to look into those two. It will not take long. And as for tomorrow, you will have all the afternoon to look into those. It will be like the labs will be, the quizzes will be like only taking half an hour or so in the end once you have your answers. All right. Yes. Great. See you tomorrow. It's still calculating.
They're like, now we're not going.
Yeah, no. It's